will be talking about clustering techniques in X-ray astronomy and structured variability in GRS 1915 plus 105. My collaborators are Dr. Anuj Nandi from URS ISRO, Sheshadri Majumdar and Dr. Shantabhrata Das from IIT Guwahati, Dr. Samir Mandal from IIST Trivandrum, Dr. Tilak Katoch from TIFR, and Dr. C.S. Stalin from IIA. So the talk is organized as follows. First, I'll introduce the topic. Then the first part of the talk is about spectral state classification using machine learning algorithms. Then the properties of GRS 915 plus 105 will be discussed. And then some work on AGNs will follow. So black hole X-ray binaries, as we see here, an artist's depiction of a low mass X-ray binary. It has a secondary star from which matter is being accreted onto the primary black hole. And the black hole can have jets also. So these are low mass X-ray binaries and high mass X-ray binaries are classified based on the mass of the secondary star. If it is a high mass star, about 10 solar mass or so, it will be a high mass X-ray binary. Otherwise, it will be a low mass X-ray binary. Now, from various space-based instruments, we get X-rays in the range of 0.3 to 200 keV, and we can study more about these sources from these X-ray signals. So, if we observe an X-ray binary source, it will be in quiescent state for a long period of time. So, then the black hole X-ray binary will get into an outburst phase. And during the outburst, the X-ray flux will be very high. And as you see here, there are two figures shown. These are both light curves of the outburst profile. And firstly, from the quiescent state, we will suddenly have an increase in flux, and then it remains high for a certain period of time. And after that, the flux slowly decays. And this outburst, it will be divided into several classes called low hard state, hard intermediate state, soft intermediate state, high soft state. Then the decay phase, again, where we have soft intermediate state, hard intermediate state, and low hard state. So the different sources show different outburst profiles. As we can see here, on the right-hand side, it is a slow rise and slow decay. So the sources on the left are XTEJ 1859 plus 226, 1999 year outburst. And on the right-hand side, it is the IGRJ 17091 minus 3624. It's 2016 outburst. Now, during the outburst, there is a hardness intensity ratio versus flux, which is called the Q diagram. And the Q diagram starts at the beginning of the outburst, it starts at the right bottom and it remains in hard state. Then the hardness ratio, which is the ratio of flux in higher energy to the lower energy band. And then the hardness decreases as it enters into the hard intermediate state, following which the hardness further decreases and it enters into the soft intermediate state. And during the transition from hard intermediate state to soft intermediate state, we can see radio flares. And after soft intermediate state, it enters into the high soft state. And then the rising phase is complete. Then the hardness again, it starts increasing as it enters into the decay phase. Firstly, there will be soft intermediate state decay, followed by hard intermediate state decay, and then low hard state decay. This figure is also called a turtle diagram. Now, from these Q diagrams, we can classify the spectral states, and this has been done manually so far. We have to consider different parameters, and based on that, we classify this. Now, we can also use machine learning unsupervised algorithms. So we have k-means clustering and hierarchical clustering. So firstly, I'll mention about the k-means clustering. So here, suppose we have n parameters and we have an n-dimensional space of parameters within which the data points are distributed. So first, we have to know how many clusters we require. So that can be obtained by prior knowledge from manual analysis. We will know what is the number k, or we can obtain it from something known as within cluster sum of squares. That I'll explain in the next slide. So once we choose the number of clusters that are required, we will randomly choose k centroids. So k is the number of clusters required. We choose k centroids, and these are randomly chosen. For example, on the right hand side, I have labeled 1. There we have 8 points, and we randomly choose centroids C1 and C2. And then we find distance of every point from C1 and distance of every point from C2. Then we associate all the points nearer to C1 to the red cluster and the points nearer to C2 to the green cluster. So the second figure here we have C1 and all nearby points in red cluster, C2 and all nearby points in green cluster. And then once the first step in clustering is done, we find the mean of the data points within C1 and mark it as a cross here in 3. And similarly, the mean of data points in C2 is marked as a cross here. This point is then made the new centroid. So with the new centroid, we again repeat the process of associating all the nearby points to that cluster. So everything near the red cross is grouped into the red cluster in label 4 here. And then all that is near to the green point is made into associated with cluster green. So this process repeats until we have consistent results. So this is how k-means clustering proceeds, and we can do it for an n-dimensional space also. So in last slide I mentioned we can choose the number of clusters by something called within cluster sum of squared distances. So we change the number of clusters from 4 to 20, and we run the k-means clustering algorithm, and for each result we find the within cluster sum of squared distance, that is the distance from the centroid to all the points in that cluster. We find that out and we sum. So from this, this is called the elbow method. We want to find the point where the WCSS starts to vary gradually, or we can plot the differentiation of this in the lower panel, and where it is almost getting a constant value, that point we can take as the number of clusters. Now the second method we use is called hierarchical clustering, and in hierarchical clustering we start by considering each data point as a cluster. So on the right hand side I have given there are A, B, C, D, E, F. These are the data points, and we consider each of them as a cluster to start with. Once that is done, we find the nearest 2 points. So B and C are nearby, we combine them into BC, and D and E are nearby, we combine them into DE. So at this stage we have A, BC, D and F, 4 clusters, and we proceed like this by accumulating the nearby points into the cluster, and we will stop at the desired number of clusters. So if we want only 4 clusters, we can stop at A, B, C, D, E and F. So this is how hierarchical clustering proceeds. But the problem with hierarchical clustering is that once it is made into a cluster, we cannot remove it from the cluster. But in k-means clustering, as the centroid keeps changing, we can associate the point to different clusters until we get consistent results. But here that is not possible. So on the left hand side top, we are seeing the Q diagram for XTJ 1859 plus 226, and left hand side bottom panel I show the parameters used for classification. So we have the total flux in the top panel, hardness ratio in the second panel, the photon index from spectral modeling in the third panel, and the inner disk temperature in the fourth panel. And in the first panel, in blue color, I have shown the observations where a type C low frequency QPO was observed. So all these parameters are given as inputs to the k-means clustering algorithm. And from them, from that, after the algorithm is run, we get the result shown in the right top. So here, if you compare it with the figure on the left top, the two Q diagrams are slightly different in the sense that on the left hand side, low Hart state or LHS was the entire right hand side of the Q diagram, but on the right hand side, after clustering, we get only one point in the low hard state, and then the others are associated with the hard intermediate state, because in the parameter space, these 2 points in the hard intermediate state, the second and third points, they are actually more closer to the hard intermediate state points than the low hard state points. So it is classified like that. And below on the right hand side bottom, we show the outburst profile after classification. Now, once we do a classification, we have to have some quantitative measures on how good the classification was. So in a binary case, we have the figure on top. It is called a confusion matrix. And here we have, suppose we have tested something for positive, and if it is positive and classified positive, then we call it a true positive. And if it is negative and classified negative, we call it a true negative. And if it is actually negative, but it is classified as positive, we call it a false positive. And similarly, false negative. So once we have all these things, once in the main diagonal will be taken, that is all the true detections, and divide by the total number of detections, that gives us the accuracy. And if we are, and then we have a measure called precision, that is true positives divided by true positive plus false positives. So consider the case where emails are filtered into spam and ham. So if we have a false positive, that means we say that a mail is spam even if it is not spam. So that is a case that we should reduce. So precision, high precision means there are minimum 4 false positives. And recall or sensitivity is another measure. And there we have we take into consideration the number of false negatives. So it is true positives by false negatives. So consider a case where a person is checked for diagnosed for a disease, and he actually has a disease, but it is shown as false negative. It is shown as negative. So it is a false negative case. So in such cases, this recall or the sensitivity should be better. In order to accommodate both these measures, we use something called F1 score, which is the harmonic mean of precision and recall. So here is the confusion matrix for the k-means clustering of the Q diagram. And here we can see that most of the cases are detected, are in the main diagonal and detected correctly. And then there are some discrepancies. For example, in the x-axis, there is soft intermediate state decay. That is the manual classification. So 6 of those are now classified using the clustering into high soft state. So there is this difficulty between classifying soft intermediate state and soft intermediate state and high soft state. So this is better when this is difficult to classify manually, so we can rely on machine learning methods to classify this. And I have carried out this clustering algorithm, k-means clustering, for a different outburst. Here we are seeing 4 outbursts of the source GX339-4 during its RXT era. On the left top is 2002 year outburst, 2004 outburst on right top, left bottom we have 2007 outburst, and right bottom we have 2010 outburst. And now in this page we can see k-means clustering results for the source MaxEJ1535-571 and IGR J1791-3624 on the right. So IGR was giving better results with hierarchical clustering, and all other cases the better result was from k-means clustering. And the corresponding outbursts, their precision, accuracy, and F1 score are shown here in the table. And in most cases, we got accuracy above 80%. Now, the second part of the talk, I'll talk about the X-ray properties of the source. GRS 1915 plus 105. So GRS 1915-105 is a very remarkable source as it has shown different variability classes in its light curves. So when we observe, for example, the second panel here is called rho class variability. The third panel is kappa class variability. And so such structured variability is observed in its light curve. And the actual reason behind this is not yet known. So this source was discovered first in 1992, and then from 1992 to 2018, it remained X-ray active. It was always giving high fluxes in X-rays, and its mass has been determined to be around 12.9 solar masses. It is at a distance of 8.6 kiloparsec and at an inclination of 65 degrees. It has shown 14 variability classes classified as per Belloni et al. 2000, and it exhibits both low frequency QPOs as well as high frequency QPOs. And we have studied this source using AstroSat data. So from 2016 year observations of AstroSat observations of GRS 1915, we have got delta class variability as shown here. On the right, we have light curves in the main panels, and in the inset, we have what is called the color diagram. Color diagram is the plot of hardness ratio 1 versus hardness ratio 2, where hardness ratio 1 is flux in 6 to 15 keV by flux in 3 to 6 keV, and hardness ratio 2 is flux in 15 to 60 keV by flux in 3 to 6 keV. So according to Belloni et al. 2000, if hardness ratio 1 is less than 1 and hardness ratio 2 is less than 0.1, it corresponds to delta class variability. So our initial observations of GRS were in delta class. And now we generate the power density spectra of different orbits over a span of 5 days. And we found that there is a 70 Hertz high frequency QPO appearing in several observations. We have shown three different orbits here. Orbit 3819 and 3860 showed high frequency QPO, and 3841 didn't show any high frequency QPO. On the right hand side, I've plotted the count rate on the top panel, and marked in red are observations where there are no QPOs observed. So when the count rate is high in delta class, we do not observe QPOs. And in the middle panel, we show the QPO frequency detected. And in the last panel, bottom panel, we show the QPO RMS. So you can see that as the count rate in the top panel increases, the QPO RMS decreases and it goes below 3 sigma significance. And then it again, as the count rate decreases, the significance improves and the RMS increases. The three vertical bars indicate observations given on the left hand side figure corresponding to orbits 3819, 3841 and 3860. Now that we have seen QPOs in different orbits, we decided to do a energy dependent power spectral analysis, and we found that in 3 to 6 keV and 25 to 60 keV bands, the QPO is not present. So the QPO is solely produced by the energy range of 6 to 25 keV. And the energy spectral modeling resulted in black hole mass and accretion rate parameters as shown here. The accretion rate was around 7 into 10 raised to 18 grams per second. The black hole mass varied from 12.5 to 13.2, and the spin was around 0.995. So it is a maximally spinning black hole. And we verified the results with EMCE algorithm, and from there we got the result as 12.85 solar masses is the mass of the black hole in GRS, and it has a spin of 0.995 plus or minus 0.001. So far we have checked the delta class variability. Now we have studied all AstroSat observations with other classes also, rho class, kappa class, omega class, and gamma class. And we use these observations because all these cases were belong to the soft state. Generally, they were soft states. So these variability classes, only the soft variability classes showed the high frequency QPO. And on the right hand side, we can see the corresponding power spectra for different classes, and the QPO feature is zoomed in the inset. And on the left hand side, within each figure, the inset is provided on the left hand top. That is the color diagram where we plot HR1 versus HR2. And we can see for delta class, it is not spread much, but in other cases, the color diagram has different profiles, based on which we classified it into gamma class, omega class, kappa class, and rho class. So for omega class alone, we see that the feature, energy dependent feature, is similar to that of the delta class that we have seen earlier. Here also, the QPO is present only in the 6 to 25 kV range. And the feature shown here has a centroid frequency of 68.09 Hertz, Q factor of 12.26, significance of 5.62, and similar results were obtained from other classes also. So the QPO was produced in the region where the energy was between 25 to 60 kV. Now that we have studied the static PDS, we decided to check the dynamic PDS. And here, this is an observation from kappa class. And on the top panel, we see the light curve in kilocounts per second. So in the kappa class, there are regular ups and downs in the light curve. So we generated the dynamic power spectra with 32-second interval length, and we see that corresponding to every ups in the light curve on the top panel, we have in the second panel high power corresponding to 70 Hertz. So whenever the count rate goes high, we are having a QPO, a high frequency QPO. And during the dips, the QPO is not present. And the hardness ratio 1 that is plotted here, it also follows the light curve profile, and hardness ratio 2 is almost a constant. Now, so the timing analysis is done with 32-second interval length. Now we also carried out the energy spectral analysis for every 32 seconds. So we generated the energy spectra for every 32 seconds within the observation and modeled it with a thermal Comptonization model. And here, if we check the first panel during a dip, we have the corresponding gamma NTH, that is the photon index of the thermal Comptonization model, and that is high. So during every dip in the light curve, we have a high gamma. Higher gamma corresponds to softer states. So all the dips here correspond to soft state, softer spectra, and all the ups in the light curve corresponding to harder spectra where gamma is low. Now this is the case for omega class, and in omega class also we see the same features. That is, we see during dips there are no QPOs, during ups there are QPOs, and where there are QPOs we have a harder spectra where gamma is low, and the norm NTH in the lower panel, in the last panel, is high. So during the presence of high frequency QPOs, the thermal Comptonization component has high norm. So we can conclude that it is a Comptonized corona that is oscillating, that results in the production of these high frequency QPOs. And we also carried out broadband spectral results for the entire observations. And here we can see the gamma is intermediate in range between 2.29 to 2.55. It is because we are considering all the dips and the ups together. And we also required an additional power law. So apart from the Comptonized corona that is producing the high frequency QPOs, there is an extended corona that is represented by the power law component. And the power law photon index are around 3 to 3.1 to 3.2. We can see that here the luminosities are provided in this table. So the luminosity of the entire observation is around 0.1 to 0.25 for kappa, omega, and gamma classes. And during the dips, that means in the previous figure here, from the light curve, we took all the dips together and co-added them. And similarly, we took all the ups together and co-added them. And then found out the luminosity of the dips, and it is 0.07 to 0.09, during which no QPO is observed. And then all the ups are taken together and they are co-added, and we found luminosity, and it is around 0.15 to 0.26. So once this is done, we replaced from the model, which is power law plus NTH-COM, we removed NTH-COM, and instead of that, we use the disk PN model. So using disk PN model, we found the inner radius of the disk, and that is given in the last column of the table. And we found that the inner disk radius is around 11.74 Rg to around 12.66 Rg. So this implies that it is a reasonably compact corona that is oscillating to produce the high frequency QPOs. And here we have plot flux versus thermal comptonization normalization, and it is plotted for different classes. For example, if we take the upside down triangles here, these triangles correspond to delta class, and they do not have a QPO detected during these observations. And when the QPO is detected, it is shown with the triangle that is pointing upwards, and there we have both the flux and the norm greater than the others. And this property is there for all other classes as well. The squares indicate omega class. In all omega classes, we have detected high frequency QPOs. And the color bar indicates gamma photon index. So when QPO is detected, gamma is in the intermediate range. Then we have done studies on AGN variability using XMM Newton data. So this is the light curves and hardness ratios for PMNJ 0948 plus 0022. For variability analysis, we found out the F variance. It is calculated as root of S square minus sigma bar square by X bar, where S square is the sample variance, X bar is the mean count rate, sigma bar square is the mean square error. And so F variance is a measure of the amplitude of variability that exceeds the noise in light curves. And the uncertainty in F variance is calculated using formula 2. Here we have tabulated the F variance for different energy bands, the soft energy band from 0.3 to 2 and hard energy band from 2 to 10. It is generally observed that in 2 to 10 kV range, the variability is more than that in the softer state, the softer energy range. And we have also modeled AGN spectra with XMM Newton. Here we have shown REJ 1034 plus 396 and PMNJ 0948 plus 0022 spectra. Here the spectral parameters are tabulated. For the first case with Markarian 493, the photon index is around 2.2 to 2.5, and a disk was not required to model this. For the other two sources, a disk also was required to model the energy spectrum. And when we replace the power law with the thermal Comptonization component, the results didn't vary much. The photon indices were almost within the same range. And we are currently trying to model the broadband energy spectra of Blazars using AstroSat S60 and LAXPC. So here the source is faint and is very much dominated by the background. So we have to estimate the background from the 50 to 80 keV energy swings, where the counts are relatively steady. And we have used only data from the top layer of LAXPC for this. So to conclude, we have used machine learning for spectral state classification of black hole binaries. We used clustering algorithms, namely k-means clustering and hierarchical clustering, of which k-means clustering was found to be better than hierarchical clustering. And we studied the characteristics of high frequency QPOs of GRS 1915 plus 105. We infer that there is an extended corona besides an oscillating corona that produces the high frequency QPOs. The mass of the source was determined to be between 12.44 and 13. The spin varies from 0.90 to 0.997. HFQPOs were observed only within 6 to 25 keV across all variability classes. And a dynamic analysis of both energy spectral and power spectral parameters were done to understand the generation of HFQPOs. The non-dip luminosities exceeded 0.15 Ldetected, during which HFQPOs were present, and the inner radius of the disk is 12 Rg, around 12 Rg, which implies that it is a compact corona that is oscillating to produce the high frequency QPOs. So these are the associated publications. And for the next work, we are planning to do signal processing techniques to classify structured variability in X-ray binaries, variability in AGNs. So we have currently correlated the narrow line Seifert galaxies database with the XMM Newton, and we have found around 130 sources for which we are planning to carry out the variability analysis. Then shock strength as a function of QPO RMS, and broadband spectral modeling of Blazars using AstroSat.
Okay. Thank you, Sreehari.
Thank you.
Is there any question? You can those who want to ask question can unmute and ask. Sreehari, probably you can switch on your video so that people can see you. Are there any questions for the speaker? There's absolute silence. Hello. Okay. I have one question. It's a very naive question. I'm not working in the field. Can you go back to one of your slides where you display the power spectrum at that certain peaks? Can you go back to a dynamic spectra you display? Maybe go back.
No. Dynamic spectra.
Yes, yes.
Okay. This one?
That's before this. Yeah, this the one before this. It's a very naive question. See, in this, no, the next one.
This one?
No, the next one. Actually, you skipped this one. Yes, dynamic spectro-temporal parameters K class.
Yes.
See on the second panel where you are displaying the power as various frequencies, that you see that there are places where the power is relatively low, 1 to 4th and 8th. Is there any another where your cursor is somewhere? The strength is low relatively compared to the other places where it is peaking, the power is more. Is that anything significant or?
So you're saying this particular part
is as well as the other one. After 3 or 4 peaks, there is another one. That is where the strength is low.
Okay.
Can you move your cursor horizontally? Because after there are 4 peaks, again there is a strength is very low. Is that any significant, or is something which can be ignored?
No, what we have observed here is that only during the high counts in the light curve, we are observing the high frequency QPO. So during the dips, they are not there.
Yeah, that is obvious. That is clear. But there are some high counts where there is power is little bit low relative to others.
Yes, the reason for that is we are not clear why that happens.
Okay.
But the general trend we observe that during high counts we observe the QPOs. Still we can see that there is some power, but it is not that high.
Yeah, relatively compared to other powers, it is relatively low. I mean, it is repeating again after 4 peaks. Again, it is repeating. Maybe if you have more time sequence data, it may repeat. I was just wondering whether you thought about it, or is it something which you are not paid in?
Okay, I'll check about that.
Okay.
Yeah, so I have one question.
Okay.
Yeah, so can I ask one question?
Yes.
Yeah, so hi Sreehari, so can you go to your slide number 3? Something or 3, where you showed your this flux variation with time.
This one?
Yeah, this one. Yeah. So yeah, I can see in your left plot that flux is decreasing and then again going up, then again going down, and it is showing some ups and downs. No, after some time, say around 60 days, and then again another 60 days. So can you explain why this is suddenly going up after a certain time, like periodically?
It is generally observed that during the decay phase, the count rate will keep on decreasing. So
yes,
in few sources we can see some differences. So that may be related to the accretion rate.
So accretion rate means change in accretion rate?
Yes, change in accretion rate may result in higher luminosity.
Yeah, so but I'm curious why it's not going down. So you can see it's like periodic. Yeah, every 60 days. Yeah.
But the general trend is that it decreases. So this can be seen in some sources where it so the actual physics behind it is not yet understood.
Okay. Okay, thanks, sir.
Okay.
Are there any other questions for a speaker? Okay, if there are no more questions, let us thank the speaker for the interesting talk. Thank you, Sreehari.
Thank you. Thank you.